Hello everyone, my name's Iman. Welcome back to my YouTube channel. Today we're going to tackle a practice problem set that relates to our lecture on waves and sound. Let's go ahead and get started with problem number 1. Problem number 1 says an opera singer has two precisely identical glasses. The singer produces as pure a tone as possible and shatters the first glass at a frequency of 808 hertz. The singer then sings a frequency of 838 hertz in the presence of the second glass. The second glass will likely blink. A says shatter after a longer amount of time because the applied frequency is higher. B says shatter after a shorter amount of time because the applied frequency is higher. C says not shatter because the applied frequency is not equal to the natural frequency of the glass. And D says not shatter because higher frequency sounds are associated with more attenuation. In this problem, we're analyzing the behavior of two identical glasses when subjected to specific sound frequencies produced by this opera singer. Now, the first glass shatters at a frequency of 808 hertz, indicating that this is the resonant frequency or the natural frequency at which it vibrates most easily. Resonance occurs when an external sound matches the natural frequency of an object, thereby amplifying vibrations and potentially leading to structural failure if the amplitude is high enough. This phenomenon explains why the first glass shatters when the singer produces a tone at 808 hertz. Now, the singer attempts to shatter the second identical glass by singing at a different frequency, a frequency of 838 hertz. Because these glasses are precisely identical, we can assume they share the same natural frequency, which is 808 hertz. However, the new frequency that's applied to the second glass, that frequency of 838 hertz, that doesn't match its natural frequency. When a frequency does not match an object's natural frequency, resonance doesn't occur, meaning that the vibrations induced in the glass are not amplified to the same extent. As a result, the amplitude of the vibrations in the second glass will remain too low to cause any structural damage or any shattering. And this leads us to conclude that the second glass will not shatter because the applied frequency, 838 hertz, doesn't match its natural frequency of 808 hertz. And without resonance, the glass is not going to shatter. And that makes the correct answer choice C. The second glass will likely not shatter because the applied frequency is not equal to the natural frequency of the glass. Awesome. Let's move on to problem 2. Problem 2 says a child is practicing the first overtone on a flute. If the child's sibling covers one end of the flute for a brief second, how will the sound change, assuming that the new pitch represents the first overtone in the new setup? Now, before we attempt to answer this problem, I want to discuss this word, overtone. An overtone is any frequency above the fundamental frequency, above the first harmonic. The first overtone is the next frequency after the fundamental frequency. So in an open pipe, the first overtone is synonymous to the second harmonic. And in a closed pipe, where we only have odd harmonics, the first overtone corresponds to the third harmonic. So overtone simply refers to the next frequency, regardless of the harmonic sequence specific to the system. Okay, this is going to be really important because in this problem, we're examining how the pitch of a flute changes when one end of the flute is covered. So initially, the child is practicing the first overtone of a flute, which is an open pipe. That means both ends are open, and that allows sound waves to form standing waves with nodes and antinodes. For an open pipe, the fundamental frequency, which is the first harmonic, that occurs when there is 1/2 wavelength along the length of the pipe. And the first overtone, aka the second harmonic for an open pipe, it occurs when there is a full wavelength. To remember that, we just need to recall our equation for an open pipe. The wavelength is equal to 2L divided by N, where L is the length of the pipe, N is the harmonic. So when we are dealing with the first overtone for an open pipe, we're dealing with the second harmonic. So N is equal to 2. And you have 2L divided by 2, that is equal to L. So the wavelength is equal to L for the second harmonic, aka the first overtone in an open pipe. Okay, keep that in mind. Now, when one end of the flute is briefly covered, then the configuration changes. It changes from an open pipe to a closed pipe where you have one end that's closed off. In a closed pipe, the standing wave pattern is different because one end of the pipe must have a node, which is a point of no displacement, while the other end has an antinode. This is the point of maximum displacement. In a closed pipe, the fundamental frequency is lower because only 1/4 of a wavelength fits into the length of the pipe. Consequently, the overtones or the harmonics of a closed pipe are not integer multiples of the fundamental frequency like they are in the open pipe. We discussed this in lecture. Instead, only odd harmonics are allowed in a closed pipe. So keeping that in mind, the first overtone for a closed pipe is actually the third harmonic. So here in our closed pipe, we're dealing with our first overtone, which is equivalent to the third harmonic. Now let's write out our relationship for closed pipes between wavelength, length of pipe, and harmonic. For a closed pipe, the wavelength is equal to 4L divided by N. For the first overtone in a closed pipe, N is equal to 3 because the first overtone is the third harmonic in a closed pipe. So now we have 4L divided by 3, and now we have our relationship between wavelength, all right, and length of pipe. 4L divided by 3. Now we can take these expressions that we have for our first overtone in an open pipe and our first overtone in a closed pipe, and we recognize something really important here. The wavelength increases going from open pipe to closed pipe. Now, if the wavelength is being increased, what happens to the frequency? Wavelength and frequency, they have an inverse proportion. They're inversely proportional. So an increase in wavelength actually corresponds to a decrease in frequency. And we want to know this relationship because frequency is directly related to pitch. And our question is, how will the sound change, assuming that the new pitch represents the first overtone in the new setup? If we know that going from the first overtone in an open pipe to the first overtone in a closed pipe results in an increase in wavelength, and that results in a decrease in frequency, now we can make a statement about the pitch. Since frequency is directly related to pitch, higher frequency corresponds to higher pitch. The pitch is going to decrease when the pipe changes from open to closed. And that makes the correct answer for problem 2, answer choice B. The pitch of the sound will go down. Fantastic. Next up, we have problem 3. Problem 3 says, which of the following is necessarily true regarding frequency, angular frequency, and period of a given wave? Before we go ahead and read our options, let's recall that the frequency of a wave refers to the number of cycles the wave completes per second, and that's measured in hertz. The period, denoted as capital T, this is the time it takes for one complete cycle of the wave, and it is the reciprocal of the frequency. So we can write that period is equal to 1 divided by frequency. Now, the angular frequency, this is another way to describe the wave's oscillation rate, but it uses radians per second instead of cycles per second. The relationship between angular frequency and frequency is given by this equation. Angular frequency is equal to 2 pi multiplied by frequency. This equation shows that the angular frequency is equal to 2 pi times the frequency. Since 2 pi is a constant greater than 1, it follows that the magnitude of the angular frequency will always be larger than the magnitude of the frequency. Let's keep all that information in mind as we go through each option. A says the magnitude of the angular frequency is larger than the magnitude of the period. Now, this statement is incorrect because the relationship between angular frequency and period is not directly about magnitude. Angular frequency relates to frequency, not period, through this equation right here. Additionally, since period and frequency are inversely related, we cannot make a simple magnitude comparison between angular frequency and period based on the given information. So answer choice A is not correct. B says the product of the frequency and period is equal to the angular frequency. This statement is incorrect. The product of the frequency and the period is actually 1 because frequency is equal to 1 over t. So if you're going to multiply period by frequency, you're just multiplying 1 over frequency multiplied by 1 over period, and that's just going to equal 1, not the angular frequency. All right, so B is incorrect as well. What about answer choice C? This says the magnitude of the angular frequency is larger than the magnitude of the frequency. This statement is actually correct. Since we said that angular frequency is equal to 2 pi multiplied by frequency, and we also said that 2 pi is a constant greater than 1, then we can say confidently the angular frequency will always have a larger magnitude than the frequency. And the correct answer is in fact C, but we're still going to read answer choice D. Answer choice D says the product of the angular frequency and period is 1. This statement is incorrect. This is going to actually be equal to 2 pi, not 1, because if you were to multiply angular frequency by period, you would multiply 2 pi multiplied by frequency, and then multiply that period, which is 1 over f, F cancels out, the frequency cancels out, and we're left with just 2 pi. So answer choice D is incorrect. With that, the answer to problem 3 is answer choice C. Again, the magnitude of the angular frequency is larger than the magnitude of the frequency. Let's tackle problem 4 next. Problem 4 says, ultrasound machines calculate distance based upon blank. A says intensity of the reflected sound. B says travel time of the reflected sound. C says angle of incidence of the sound. And D says the detected frequency of the sound. Now, ultrasound machines, they use high frequency sound waves that travel through tissues and reflect off of surfaces where there is a change in tissue density. These reflected sound waves, also known as echoes, they're detected by the machine's sensors. The key factor in determining the distance to a particular structure or boundary within the body is the time it takes for the sound wave to travel to the structure and back to the ultrasound probe. The ultrasound machine emits a pulse, and that wave travels until it hits a boundary like the edge of an organ, where some of that sound is reflected back. The machine then measures how long it took for the echo to return. So all things considered here, the correct answer is going to be B, travel time of the reflected sound. I do want to discuss why all the other answer choices are incorrect, though. A says intensity of the reflected sound. Although intensity could be used to measure distance, time of travel is an easier indication, and it's most commonly used by ultrasound machines. C says angle of incidence. This can be used to position various structures on the screen of an ultrasound, but it's not used to calculate distance. D says the detected frequency of the sound. The apparent frequency is only used in Doppler ultrasound, but it's not used to calculate distance. So again, the correct answer to problem 4 is B. Ultrasound machines calculate distance based upon travel time of the reflected sound. Onward to problem 5. Problem 5 says, the period for a certain wave is 34 milliseconds. If there is a Doppler shift that doubles the perceived frequency, which of the following must be true? Let's start with statement 1. Statement 1 says the detector is moving towards the source at a velocity equal to the speed of sound. While movement towards the source would increase the perceived frequency, moving at the speed of sound would create an extreme Doppler shift, likely resulting in an infinitely high frequency for an idealized case. Therefore, this extreme speed is really unnecessary to just double the frequency, and the statement is not necessarily true. What about statement 2? Statement 2 says the source is moving towards the detector at a velocity equal to half the speed of sound. Now, again, while this motion would also cause a Doppler shift, it's not specified that moving at precisely half the speed of sound would result in doubling the frequency. The Doppler effect depends on both the relative velocities of the source and detector, so without precise calculations, we cannot conclude that this exact speed would double the frequency. So this statement is also not necessarily true. Statement 3 says the perceived period is 17 milliseconds. Okay, so we're given that the wave has an original period of 34 milliseconds, and then we're told the Doppler effect causes the perceived frequency to double. Since the period and the frequency are inversely related, frequency is equal to 1 over t, or you can write this as t is equal to 1 over f. Doubling the frequency would actually cut the period in half. So the initial period of the wave is 34 milliseconds. If the perceived frequency doubles, then the new perceived period will be 34 milliseconds divided by 2, and that's going to be equal to 17 milliseconds. So statement 3 is actually correct. So statement 3 is the only statement so far that is true. Statement 4 says that the perceived period is 68 milliseconds. So we've already calculated that the perceived period is equal to 17 milliseconds, not 68. So statement 4 is incorrect. The only statement that is true is statement 3. So the correct answer to problem 5 is answer choice A. Beautiful. Let's move on to problem 6. Problem 6 says, if the speed of a wave is 3 meters per second and its wavelength is 10 centimeters, what is its period? To determine the period of the wave, we have to start by understanding the relationship between wave speed, wavelength, frequency, and period. The speed of a wave is equal to the frequency of the wave multiplied by its wavelength. Now, we're ultimately concerned with calculating the period, and there is a relationship between frequency and period. Frequency is equal to 1 divided by the period. So we can go ahead and replace the frequency term with this term right here. Now, we have that the speed of the wave is equal to 1 over the period multiplied by the wavelength. Our ultimate goal is to figure out the period, so let's isolate the t variable here. T, or the period, is going to be equal to wavelength divided by the speed of the wave. Now, the wavelength is equal to 10 centimeters. We want to convert this to meters so that the units cancel out appropriately with the wave speed. 10 centimeters is equal to 0.1 meters. And then this is divided by the speed of the wave, which is equal to 3 meters per second. You notice here, meter units cancel out. We're left with seconds. 0.1 divided by 3 is equal to 0.03 seconds. So the period is equal to 0.03 seconds, which aligns with answer choice B. The correct answer for problem 6 is B. Let's do problem 7. Problem 7 says, what is the angular frequency of the third harmonic in a pipe of length 1.5 meters with one closed end? Note that the speed of the sound is approximately 340 meters per second. Now, the wavelength of the nth harmonic in a pipe with one closed end, it can be calculated using this formula. Wavelength is equal to 4L divided by N, where L is the length of the pipe and N is the harmonic number. For a closed pipe, there's only going to be odd values that are allowed for the harmonic number. Now we're given the length is 1.5 meters, and we're told that we are concerned with the third harmonic, so N is equal to 3. Let's go ahead and plug these values in. 4 times 1.5 meters divided by 3. 4 times 1.5 is equal to 6. 6 divided by 3 is equal to 2, and our units are meters. So the wavelength of the third harmonic is equal to 2 meters. Now that we know that, we can calculate the frequency of the third harmonic. The frequency of a wave is related to its speed and its wavelength. It's equal to its speed divided by the wavelength. Now, we're given the speed of the wave. The speed of sound is approximately 340 meters per second. And we just calculated the wavelength to be equal to 2 meters. So 340 meters per second divided by 2 meters, this is going to be equal to 170 hertz. And that's because our units are 1/seconds. So we can just write this as hertz. Now we need to convert frequency to angular frequency. Angular frequency is equal to 2 pi multiplied by frequency. So this is going to be 2 pi multiplied by 170 hertz. Now noticing our answer choices here, we have 170, we have 170 pi, we have 340, and 340 pi. So it doesn't seem like they multiplied pi out. So all we have to concern ourselves with is multiplying 2 by 170. That's equal to 340. And we can keep pi as is. This gives us an angular frequency of 340 pi radians per second. And that aligns with answer choice D. So the correct answer for problem 7 is D. We first determined the wavelength of the third harmonic, then we calculated the frequency of the third harmonic, and then we converted frequency to angular frequency. Let's do problem 8 next. Problem 8 says, a certain sound level is increased by 20 decibels. By what factor does its intensity increase? We're going to set I initial as the intensity before the increase and I final as the intensity after the increase. Then we're going to use the equation that relates sound level to intensity to get the ratio of initial intensity to final intensity. That equation says that the final sound level is equal to the initial sound level plus 10 log of our final intensity over our initial intensity. Then we're going to subtract our initial sound level from both sides to get our final sound level minus our initial sound level. That's equal to 10 log final intensity over initial intensity. Now this final sound level minus initial sound level, that's equal to 20 decibels. That's what we're given in the problem. 20 decibels is equal to 10 log I final over I initial. We're going to divide both sides by 10, and that gets us 2 is equal to log final intensity over initial intensity. Now to get rid of this log, we're going to set 10 raised to all of this on one side, and we're going to do the same thing to the other side. This gets rid of our log on the right side of our expression. And now what we have is 10 raised to the power 2, which is equal to 100. That's equal to our final intensity over our initial intensity. So a certain level, sound level, is increased by 20 decibels. By what factor does its intensity increase? By a factor of 100. So the correct answer for problem 8 is C. Amazing. Let's move on to problem 9. Problem 9 says, in some form of otosclerosis, the stapedial footplate, which transmits vibrations from the bones of the middle ear to the fluid within the cochlea, can become fixed in position. This limits the displacement of the stapedial footplate during vibration. Based on this mechanism, which of the following symptoms would most likely be seen in an individual with otosclerosis? A says an increase in the perceived volume of sounds. B says a decrease in the perceived volume of sounds. C says an increase in the perceived pitch of sounds, and D says a decrease in the perceived pitch of sounds. Now, saying that the stapedial footplate has limited displacement during vibration is just another way of saying that the amplitude of the vibration has been decreased. Because amplitude is related to intensity, and intensity is related to sound level, the perceived sound level, aka the volume, will be decreased as well. And so the correct answer here is going to be answer choice B. There's going to be a decrease in the perceived volume of sounds. Pitch is related to the frequency of a sound, but it's not related to amplitude, which is why C and D are not correct answers for this problem. Again, 9 is B. Let's tackle problem 10. Problem 10 says, if two waves with the same frequency are 180 degrees out of phase, what is the amplitude of the resultant wave if the amplitudes of the original waves are 5 centimeters and 3 centimeters? When two waves are out of phase by 180 degrees, one wave's peak aligns with the other wave's trough, and vice versa. So in this situation, the waves are going to interfere destructively, meaning they're going to partially or completely cancel each other out depending on their amplitudes. In this problem, we're given two waves with amplitudes of 5 centimeters and 3 centimeters. Since they are 180 degrees out of phase, the amplitude of the resultant wave is found by subtracting the smaller amplitude from the larger amplitude. So it's going to be 5 centimeters minus 3 centimeters, which gives us 2 centimeters. The final answer here is going to be 2 centimeters, which is answer choice A. This result occurs because the larger wave partially cancels the smaller wave, leaving a resultant wave with an amplitude equal to the difference between the two. Again, the amplitude of the resultant wave is 2 centimeters, and the correct answer is A. Let's move on to problem 11. Problem 11 says, a student is measuring sound frequencies from the side of a road while walking east. For which of the following situations could the student determine that the difference between the perceived frequency and the actual emitted frequency is 0? To answer this problem, we're going to need to consider the Doppler effect. The Doppler effect describes how the perceived frequency of sound changes when there's a relative motion between the source of the sound and the observer. When the source and the observer are moving towards each other, the perceived frequency increases. On the other hand, when they're moving away from each other, the perceived frequency decreases. However, if there's no relative motion between the source and the observer in terms of distance, then the perceived frequency remains the same as the emitted frequency, resulting in no Doppler shift. So let's keep that in mind as we work through our options. A says, a plane flying directly above the student from east to west. So in this case, the plane is moving perpendicular to the student's direction of travel. Although the plane is moving relative to the student, it's not moving closer to or further away from them along their line of travel. Despite this perpendicular motion, there may still be a slight Doppler shift due to the relative velocity component, so the perceived frequency might not exactly match the emitted frequency. Answer choice A is incorrect. B says a police car passing the student with its siren on. So here, the police car is passing by the student, which means it's moving closer to them at first and then moving away. This relative motion along the line of travel would produce a noticeable Doppler effect because the perceived frequency is going to be higher as the car approaches, and then it's going to be lower as it moves away. Therefore, there's going to be a difference between the perceived frequency and the actual emitted frequency, and B is incorrect. C says a person playing piano in a house on the street. So In this case, the piano is stationary, but the student is moving. So although the sound source isn't moving, the student's movement towards or away from the sound may cause a Doppler shift. As the student moves east past the house, there could be a slight Doppler effect as they move towards and then away from the house. So C is also incorrect. D says a dog barking in a car that moves east. So in this case, both the student and the dog in the car are moving east. Since they're traveling in the same direction with no change in relative distance, there's no relative motion along their line of travel. So as a result, there would be no Doppler shift and the perceived frequency would match the emitted frequency exactly. So the correct answer for 11 is in fact D. Beautiful. Let's tackle problem 12 next. Problem 12 asks, in which of the following media does sound travel the fastest? A says vacuum, B says air, which is a gas, C says water, which is a liquid, and D says glass, which is a solid. Now, sound is a mechanical disturbance propagated through a deformable medium. It's transmitted by the oscillation of particles parallel to the direction of the sound wave's propagation. So as such, sound needs matter to travel through. A says vacuum. In a vacuum, there are no particles to vibrate, so sound cannot travel at all. Without a medium to propagate the wave, sound cannot be transmitted through a vacuum. So we can go ahead and eliminate answer choice A. Now, B says air, which is a gas, C says water, which is a liquid, and D says glass, which is a solid. The speed of propagation is fastest in solid materials, followed by liquids, and then it's the slowest in gases. And the reason for that is because the speed of sound, it depends on two main factors, the density and the elasticity of the medium. In general, sound travels faster in materials where particles are closer together and more tightly bound, allowing vibrations to transfer more quickly from particle to particle. So with that being said, the correct answer for 12 is going to be D, glass. Glass is a solid where particles are densely packed and the medium has high elasticity. Wonderful. Let's do problem 13. Problem 13 says, shock waves have the greatest impact when the source is traveling blank. A says just below the speed of sound, B says exactly at the speed of sound, C says just above the speed of sound, and D says well above the speed of sound. Now, to understand when shock waves have the greatest impact, we need to consider how shock waves form and their relationship with the speed of sound. Shock waves occur when an object moves through a medium at or above the speed of sound. As an object approaches the speed of sound, sound waves produced by the object begin to compress because they cannot travel faster than the object itself. This compression leads to the buildup of wavefronts, creating a high-pressure region around the moving object. Now, when an object travels exactly at the speed of sound, it generates a maximum buildup of compressed sound waves. This compression forms a sharp pressure front, commonly known as a sonic boom. At this precise speed, the sound waves produced by the object align in such a way that they superimpose on one another, creating a large and sudden change in pressure that propagates outward. And this intense pressure front, it gives shock waves their characteristic impact or intensity, making them very noticeable to observers on the ground. Now, if the object travels just below the speed of sound, which is what option A says, the sound waves are not compressed to the same extent, and so no shock wave is formed. The waves are still able to propagate ahead of the object, but there's no sharp buildup of pressure. If the object travels just above the speed of sound or well above the speed of sound, it will still create shock waves, but the impact of the shock waves tends to be less pronounced than at exactly the speed of sound. At these higher speeds, the shock wave's angle changes and the pressure differential between the front and back of the shock wave decreases as the object moves further away from the speed of sound. So, in short, while shock waves still occur at these speeds, their intensity and their impact are typically less dramatic compared to when the object is exactly at the speed of sound. So, in conclusion, shock waves have the greatest impact when the source is traveling exactly at the speed of sound because it creates the maximum compression of sound waves and it results in the most intense pressure front. The correct answer for problem 13 is answer choice B. Next up, we have problem 14. Problem 14 says, as a teacher approaches a student who is studying with the radio playing loudly nearby, the teacher experiences the Doppler effect. Which of the following statements remains true while the teacher moves closer to the student? To solve this problem, we need to understand the Doppler effect. And the Doppler effect states that the frequency of a wave, such as sound, changes for an observer moving relative to the source of the wave. When the observer moves closer to the source, the frequency appears higher, and when the observer moves away, the frequency appears lower. Let's keep that in mind as we read statements 1, 2, and 3. Statement 1 says, the apparent frequency of the music is increased. This statement is true. Since the teacher is moving closer to the source of the sound, which is the radio, they're going to perceive a higher frequency due to the Doppler effect. As the teacher approaches the student and the radio, the sound waves reach the teacher more frequently, effectively increasing the apparent frequency of the music. So statement 1 is true. Statement 2 says the same apparent frequency would be produced if the teacher were stationary and the student approached at the same speed. This statement is incorrect. The Doppler effect depends on the relative motion between the source of the sound and the observer. Here, the teacher is the observer, and the frequency they perceive depends on their own movement relative to the radio, which is the sound source. If the teacher were stationary and the student approached the teacher, it's not going to affect the frequency that the teacher hears from the radio because the student's movement doesn't influence the sound reaching the teacher. So 2 is false. Statement 3 says the apparent velocity of the wave is decreased. This statement is also incorrect. The speed of sound in a medium like air is constant for a given temperature and pressure, and it doesn't change due to the relative motion of the observer or the source. The Doppler effect changes the perceived frequency, but it doesn't affect the actual speed of the sound waves. Therefore, the velocity of the wave remains the same regardless of the teacher's movement. Statement 3 is false. So the only correct statement is statement number 1, which means that the correct answer for problem 14 is answer choice A. And with that, we move into our last and final problem. Problem 15 says, ignoring attenuation, how does the intensity of a sound change as the distance from the source doubles? Sound travels in waves that emanate outward in all directions from the source, creating expanding concentric spheres as they move away. The intensity of sound, which is the power per unit area, depends on the area over which the sound energy is spread. In this case, the area refers to the surface area of these concentric spheres. For a sphere, the surface area is equal to 4 pi r squared, where r is the radius of the sphere, which in this context represents the distance from the sound source. As the sound waves move away from the source, the energy they carry spreads over increasingly large spherical surfaces. Since the total energy remains constant, it has to be distributed over the entire surface area of the expanding sphere. As a result, the intensity, which is the sound power divided by the surface area, decreases as the distance r increases. And we can see that in this relationship here. This equation shows that the intensity is inversely proportional to the square of the distance. When the distance doubles, the surface area of the sphere increases by a factor of 4 because 2 squared is equal to 4. As a consequence, the intensity decreases to 1/4 of its original value because the same amount of energy is now spread over 4 times the area. That means that the correct answer for problem 15 is answer choice D. How does the intensity of a sound change as the distance from the source doubles? The intensity is 1/4 its value. So it is 1/4 as intense. And with that, we've completed the practice problem set for this chapter. I hope that this has been helpful. Please let me know if you have any questions, comments, concerns. Other than that, good luck, happy studying, and have a beautiful, beautiful day, future doctors.